Hello community! Today we have a new discovery in artificial intelligence. There is something brand new they discovered in large language model, and it is called a retrieval head. So for all my green grasshoppers, if you want to follow a 1-minute introduction, if you know everything, skip to the next minute. You know our transformer architecture, our encoder and our decoder part, and we have here attention heads. And those attention heads are crucial in the architecture of a transformer because they enable here the model to selectively focus on different parts of the input sequence, allowing it here to capture complex dependencies and relationship in our input data. Now, by employing here multiple heads, this LLM gains here more nuanced understanding of the data, leading to an improved performance in our task. And you see here from the original paper, attention is all you need, the scale dot product attention with this formula. And then you just put this here in parallel with what we call multiple heads or multiple layers. And this is all there is to it. You can see here the visual here. You have here mathematical multiplication of the matrix from the query and the key. This is here. You have here this multiplication, query and key transpose. Then you scale it here with a particular factor. Then you have a softmax operation. This is here. And then you have another matrix multiplication here of this result of the softmax with the value tensor structures. This is exactly how you calculate here the attention, and we just do this in parallel multiple times, and so we have here our multi-head attention. Now, by attending now to different parts of our input sequence, each attention head generates here a very distinct representation of the information. And if you want to know again, this is here how this is done. Now, each attention head can focus now on different aspects of our input sequence. For example, on the syntactic dependencies, on the semantic relationship, or, and this will be our topic, on the long-range dependencies if you have, for example, a 1 million context length. And this is done by a mechanism that the multi-head attention allows the model to jointly attend to information from different representation subspaces at different position of our input sequence. This is here more or less exactly how you calculate here the multi-head attention, but I wanted to tell you, we know here that they come from a different subspaces, and each subspace is specialized for a particular topic, like syntactic dependencies or semantic relationship or long-range dependencies. So this was the introduction. Now we go on with the normal stuff. So the question is, in our transformer architecture, what exactly is each attention head focusing on? Is there a difference between them? How can we strengthen them? How can we weaken them? Can we add new attention head online? Now, we know for a long time that multi-head attention is secretly here a long context processor. You see this here from end of March 2024, where the idea was, if we have a full attention with all the heads, and then we had out of pre-trained length here, let's say it is from 1 million token plus, the idea of the long head was you took the heads and then you find here some chunks that you find here in the complete length, and you allocate it more or less to certain sequence length that are normally out of the pre-trained length. A simple idea, and you see it's coming up, and in general what we know about the attention head is here, we tend to view the functionality of the feed-forward layers, as I've shown you in the chart, to be the place for storing our knowledge, and the specific attention layers to be the place for implementing all our algorithm. So we have a beautiful balance. So if you want to learn here about the feed-forward layers as the key value memories, I would recommend this particular preprint to you. And if you want to learn more about attention layers to be the place for implementing our algorithm, or in the old saying it was the induction heads. You have here from Anthropic here a beautiful preprint here from March 2022. Yeah, today we're gonna develop something completely new, but just to tell you, there's also here this insight that will be tested, and it's said here, especially here from the transformer architecture to the state space model like S4 or S6 member. They say here, so far there's no linear attention or SSM architecture, state space model architecture, that passes the needle in a haystack test to the best of our knowledge, suggesting that the full attention might be a must for long context information retrieval. And I think this is a challenging sentence, so maybe you're interested to comment on this. But now to our main study. We have here Peking University, University of Washington, MIT, University of Edinburgh, and they now found something new. They looked at all the different attention head and they said, you know, there is one specific group of attention head that I think we can explain here the long context factuality of our long context large language model. So they discovered here a very particular subset of attention heads. How have they done this? They introduced here a retrieval score. It is simply here the measure of the frequency of a head's copy and paste behavior during an autoregressive decoding. An attention head with a high retrieval score, it will be between 0 and 1, suggests that statistically across various contexts, this head is frequently copying the input tokens from the input to the output. If you want to see here the official text here, this is the screenshot from the study. Just for you, for each attention head, we calculate here a specific score for a specific frequency of a copy-paste operation that this head is doing. That's all there is to it. Now, I haven't explained needle in a haystack, so give me a second for this. We have on GitHub here, free for you, the LLM test needle in a haystack. And what is it? It places a random fact or a statement, which we call the needle, in the middle of a long context window. This is the haystack. And then we ask the LLM to retrieve this particular statement, our needle. And then we iterate over various document depths and the context length to measure, does the system find the needle? So you see, a simple needle in the haystack analysis to test here in-context retrieval ability of long context LLM, and this code works great for OpenAI, Anthropic, and Cohere LLMs. You have, however, to validate that if an answer is correctly generated by the system, it is indeed copied from the context, not from the models, from the LLM's internal parametric knowledge. Because we want to have here an input stream or an input prompt, a long input prompt, 1 million token, and we want to make sure it's from this long context prompt and not from the internal knowledge of our LLM. And now to show you here the result, and they found, and here you have, for example, if you have a long document, you have here the bottom of the document, and here you have the top of the document, and all the different discriminators. And then you have here simply the number of the tokens, 1000 token, 28,000 token, 128,000 tokens. And you see green, no problem at all. But then there are particular distances where the accuracy of the retrieval does not reach anymore the green 100%, but we have here problems. Look, 0%, 0%. So we have here a problem there, the performance, the higher the context length of the number of tokens, like here 100,000 tokens, in the old GPT-4, this was the old system, you had problems. Also, if you look at the old Claude 2.1, remember now we have Claude 3, which is much, much better. The old system with a 200,000 token length, you saw here, wow, there are quite a lot of red here. So this was in the history the reason why those systems failed to produce here the context that was hidden somewhere in the document. Great. Now let's go here to our new study about retrieval heads. You have this here, this little symbol here with retrieval head. Now they looked at this and they had the scoring. Remember, we have now here in red the score from 0.5 to 1. So those are the active retrieval heads. And they say, how many of them are in our LLM? And they looked at the Llama 2, I looked at the QN, at the Yi, and at the Mistral system, at a dense model and a mixture of expert model. And what they found, look at the red, it is about 1%, less than 1%. And from the 0.1 to the 0.5, if you take here this orange also, it's about 5%. Yeah, also about 5%. So they said in the long context transformers, our Gemini 1 million token, our Claude 3 200,000 plus token, we have special long context retrieval heads, but they are less than 5% of all the attention heads in our large language model. So if those special attention heads that the system generated itself are less than 5%, those are very precious. Beautiful. Now what they did, they said, okay, if we now mask out here the retrieval heads, if we deactivate the retrieval heads, we should see that our beautiful green needle in a haystack performance will go red. And exactly this is happening. If they mask out here top 20 retrieval heads of the LLM, the accuracy goes down to 63% and we have a lot of red, the further the context length increases of our system. This leads to failure in retrieving relevant information, especially in RAG system, and this results in factual hallucination. Please note that those retrieval heads are not here for the ability to, let's say, generate English sentences. The English language is learned by different attention heads. Those retrieval attention heads are really specialized here in the retrieval in our long context LLM. Therefore, we only have a factual hallucination, but not a linguistic hallucination. If, on the other side, you just mask out some other heads of the system, the accuracy falls a little bit, but we are here at almost 95%. So you see, those retrieval heads for information retrieval, like say in RAG system, retrieval augmented generation, those retrieval heads are of significant importance for our system. Now we can have a look here and compare here a dense transformer like here, those two with a mixture of expert system. And in red here, the solid line, you have here a mixture of expert system, a Mixtral 8x7b. Now you see compared to a Llama 2 7b with an extended augmented 80K context length, and we will talk about this in a second, you see this green line goes down significantly faster. Of course, if you have 8 experts in our mixture of experts system, you see the red line here stays almost horizontal till we reach about 20 masking of the specific heads, and then it starts to decline. Yeah, of course, we have 8 different experts. So you see, between dense transformer architecture and a mixture of expert system, there's here an interesting difference. But you see, for example, if you take here the model Yi, the 6 billion with an extended 200,000 token length, you see this is really sensitive if you mask here specific heads. The performance goes down from 100% close to 50%, just masking 5 specific heads. So there's an extreme sensitivity if you perform this needle in a haystack performance test. Great. Now, on the other side, the authors tested if the model directly generates an answer to a given query using only its intrinsic knowledge. So no going out and say, hey, I have to retrieve new knowledge. Is somewhere a database? Can I augment it with another database data and bring it back to my input prompt? If this is not the case, if the model knows the answer by heart, by its intrinsic parametric knowledge from the pre-training and the fine-tuning, then if we mask out the retrieval head, we have a less impacted performance, of course, because we don't have to retrieve here, but the model already knows it. Our body of knowledge is in the parametric knowledge. Interesting fact. So let's say, what is now our retrieval head? After all of this, can we give now a summary? So the authors of the study at MIT and Peking University showed we can design simple algorithms. And if you think, hey, I find a better algorithm, go for it. This is just the simplest algorithm they could think of. To detect here very special attention heads, they call retrieval heads, within the classical transformer architecture. What they found is that depending on the LLM model and the architecture, there are strong retrieval heads that are always active, independent of the specific content that will be retrieved. Physics, mathematics, cooking, whatever. Plus, we have weaker retrieval heads with a low retrieval score calculated, and they are dynamically activated within our LLM depending here on the specific content. And this is LLM specific. So you see, if, for example, you had, and this is now an assumption, a specific fine-tuning here on a specific domain, there is the idea that we do not know the answer yet. If those creates here our weaker retrieval heads that now are given a specific domain query, are now dynamically activating within the system. Let's have a look at this in more detail. You have here a heat map of here our retrieval heads, and this heat map is here normalized here to values between 0 and 1 here for the retrieval score. Now, on top we have a simple dense Mistral 7B model, and if I remember correctly, I think it has a context length of about 8K or something like that. And then we have here a mixture of expert system with 8 times 7 billion parameter. And now you would expect that the distribution here of the learned retrieval head is different. But look at detailed. Look at this. We have here 2 reds, we have here 2 reds. We have here red, ochre, 2 reds. Red, ochre, 2 reds. We have here at head 28, 1 red, and here also at 28, 1 red. So you see the distribution of very active of our strong retrieval heads, even if we build a mixture of expert system from our Mistral 7B, they have a very close, I don't want to call it configuration, I don't want to call it symmetry, a distribution. They have a very similar distribution here of the activated retrieval heads. So this is now interesting because this leads here to the idea, what happens if I have a model and I augment a model to get more context length, or I add fine-tuning, or I add any alignment, or I continue to pre-train my LLM. How many new retrieval heads can I create in my LLM? Now, let's have here an example. And the authors looked at the Llama 2 7B. Yes, it's an old Llama 2, sorry. And you see here the heat map here of the retrieval score, the heads, and the layer IDs. And now they took the Llama 2 and they extended here the context length. They continue to train it up to 80K context length. And now you would assume, let's say, this is a 10-fold increase here in the context length from model A to model B. Now you would assume that with a 10 times increase in the context length, the model would develop 10 times more strong retrieval attention heads in its LLM architecture, given this additional training. But look at the facts. They are a little bit different placed. Look just at the red. We have here those red and here those red. And we have here one red that's missing here, but this red is identical. And then we have 2 here. So we have 1, 2, 3, 4, 5, 6, 7, 8 hot retrieval heads in the Llama 2 7B Classic. And we have 1, 2, 3, 4, 5, 6, 7 hot retrieval head in the extended version of 80K context length. So not at all that there's a tenfold increase. They stick here with more or less the same amount of strong retrieval heads. So it even goes down 1. This explains a lot of, while those models where later on we try to improve here the context length because it was not done during the pre-training, why those models do not perform, especially on RAG system. And this gives us here a beautiful understanding why this is the case. Now, in the authors here, in the summary, they write that the same set of retrieval heads, let's say our red here, of the pre-trained base model, of the pre-trained LLM, the Llama 2, are used even if we have a later pre-training or a context extension performed on the system. Now, I would be a little bit more precise. It's not really the same set because you saw we had 8 and just 7, and it's not the absolute identical position. So I think this is better regardless of the model being then continuously additionally pre-trained, or then chat fine-tuned in addition, or then sparsely upcycled models. There's a notable consistency in their retrieval score heat maps in reference to the pre-trained base model. So this now indicates now strongly that those strong active retrieval attention heads are generated during the pre-training phase of our LLM training. Not if we continue to pre-train it, not if we fine-tune it, and not if we upcycle or augment it or extend it or whatever. This is what the authors found and published here in this particular study, Peking University, MIT, and University of Edinburgh. This would also explain a lot of other facts. So you see, identifying what all the different attention heads do in our LLM, it's really getting interesting, and we can now specialize and focus on performance improvement. And we know if we want more of them, it happens in the pre-training phase. Another insight that is absolutely amazing, and I just read this here, those retrieval heads significantly influence here the task that require a chain of thought reasoning. And I said, how is this possible? Come on, this is not true. But then I started to think with my little brain a little bit about it, and I said, okay, so whenever you have here a chain of thought reasoning complex, you need access to all the data. You retrieve a lot of data very specific to your query or to the task that you are asked to perform on the chain of thought reasoning. So if you do not retrieve all relevant data, of course you have missing data. So I understand that the performance of the retrieval head to bring in all the relevant information for my chain of thought reasoning. I said, okay, maybe I do feel that this retrieval head performance has a significant influence on the general chain of thought reasoning of the LLM system. And the authors write, the retrieval heads strongly influence here the chain of thought reasoning, where the model needs to frequently refer back to the question. So this is exactly, if we have a RAG system, the retrieval augmented part. Here our retrieval head are the workhorse. They do all the heavy lifting work that our RAG system operate and maybe will become much better in the future. So here is now, and in a short sentence, the author writes, this indicates here a complex relationship between the model's retrieval and its reasoning capability. And this is another amazing fact that you have what sounds logic if you think about it, that those two, retrieval and reasoning, are somehow connected here over the performance of our retrieval head in our LLM. It doesn't stop here, it goes on. This is an amazing paper. And the paper says, hey, you know why? We found why there's hallucination in our LLM. And I said, no way, this is not okay. However, they said, when the model fails to retrieve here in our Haystack, for example, the full needle, this means the complete sentence we are looking for. They say they found two typical errors are happening now in the system. A, if it's an incomplete retrieval, so where the retrieval head missed some part of the sentence of the information. So for example, in this example, we have a sentence, go to Dolores Park on a sunny day and eat a sandwich. And we are looking for this. This is our needle sandwich in the complete haystack. Now, if it happens that we do not have, because our LLM was not pre-trained good enough, we have an incomplete retrieval, and the retrieval heads only detect, if you want, Dolores Park on a sunny day, the retrieval head misses now part of this sentence, like eat a sandwich. It is not detected, and therefore we have now the potential that hallucination appears because some part of the information is simply missing, and the system tries to somehow, I don't want to say compensate, but yeah, it's compensate for missing data. And this is where hallucination appear, at least according to the authors. Or the second case here, complete hallucination, if the model cannot find the needle at all. So if all our retrieval heads fail and we find nothing, the needle is not detected in our haystack, the system now give me a query and no data to answer the query. The system now goes in full hallucination mode, and the retrieval head attend now in their calculation of the attention to initial token, like a token like begin of the input. Amazing. So the system, not finding anywhere to connect to, simply goes here in this example to a dummy token, to a structural token that indicates here the beginning and the end of a sequence, but not to a semantic valuable word that contains the information. Interesting to find out this system dynamics here if our retrieval heads do not perform 100%. So at the end of this, and go and read the study, I would recommend it, there is now a question. Hey, to improve our RAG system, to improve here our long context window of 1 million token length or 10 million context length with the next Gemini model, can we generate now, to increase here the retrieval performance, can we add additional retrieval heads in the architecture of our large language model? And I would deduct, reading this publication by MIT and Peking University and University of Edinburgh, that this is done primarily in the pre-training phase. If you have a pre-training data set with very long context length, with very challenging tasks, with very challenging instructions that the system has to learn on, in reasoning, in question and answer, in summarization. So the more complex and the more extended here the complexity of the system in the training data set is, the better the pre-trained model will perform later on, even without additional fine-tuning for domain-specific knowledge. So this study seems to indicate that it has to be in the pre-training data set, that the LLM detects only those patterns in the pre-training data set if the data set is complex, has a high complexity in its structure and its reasoning sequence. Only then we will get real powerful LLMs that outperform all other systems in retrieval, in RAG applications, and interestingly connected now in complex causal reasoning tasks. I am blown away by this study. I love this study. I hope I could give you a feeling of what is hidden in those pages. And maybe if you have the time, I would recommend have a look yourself. Maybe you get answers to the questions you have on your particular task. And maybe this insight help to understand you here. What is the current state of research on this topic? Although it was already published a week ago, I think this is absolutely amazing. So this is it for today. I hope it was a little bit helpful. It generated new insights, and it would be great to see you in my next video.